we're going to take a practice run through what we called the elimination game. More formally, this is called Gaussian elimination. And that's when you take a box of numbers, a matrix, and manipulate the rows in order to reach the gold standard, which is this. So the paper that I just tossed in here shows the gold standard of row echelon form, which means the more zeros there are in front, the farther down the row needs to go. And in any row, when you get to the first non-zero entry, that needs to be a 1. And so we need to change this into something that looks like this with two rules. The rules are we can interchange any two rows. That's one rule. And we can replace any row by a linear combination of any of the other rows or even itself. So you can take a row and replace it with itself multiplied by 5 or divided by 8 or whatever you want to do. You can take row 3 and replace it with 2 times row 1 plus 4 times row 2. Or you could take row 2 and replace it with row 1 minus row 2. That's it. Those are the rules. Replacing a row with a linear combination of other rows, or swapping two rows. And those are the only two rules we need to get from here to here. The strategy here is to put zeros underneath the leading 1 in the first column. So we're going to aim to put a 0 here, and we're going to aim to put a 0 here. And I can operate with a couple of different moves or manipulations at the same time as long as they don't interfere with each other. Okay? So what that means is I want this number to turn into a 0. And I can do that through any sort of multiplicative, constant, and plus minus combination of any of the numbers above it or below it, or even itself. That's a fancy way of saying, let's just suppose I took 2 times row 1 and subtracted row 2 and put that result into where row 2 sits. So in other words, 2 row 1 minus row 2 will be placed where row 2 currently sits. And similarly, to get a 0 in this spot, let's take 3 times row 1 and add row 3 and dump that result in where row 3 currently sits. Technically speaking, linear combinations of rows are constants of rows plus one another, but minus row 2 and plus negative 1 times row 2 are effectively the same thing. And so we're all friends here. We'll just write it as 2r1 minus r2. We're not changing row 1. We're borrowing it for the other manipulations, but row 1, at least for the moment, is unchanged. So now we're going to do 2 times row 1 minus row 2. So let's go down entry by entry. 2 of these minus that. So 2 minus 2. That's 0, and that's the whole reason we made that choice. And then whatever else happens, happens. 2 of those, 2 of negative 3, which is negative 6, minus negative 5 is a negative 1. 2 of those minus that, 8 minus 6. And then 2 of those minus that, 6 minus 6. And now let's do the action on row 3, which again is 3 times row 1 plus row 3, that result replacing row 3. So 3 of those, 3 plus that, makes a 0, and once more that's exactly why we made that choice. 3 of those plus that, so negative 9 plus 3 gives us a negative 6. 3 of those, 12 plus that, so 12 plus 4, 16. 3 of those plus that, so 9 plus 6 is 15. So far, so good. So we've introduced zeros in those two spots. And again, remember the gold standard. We've now put zeros in these two places. That's good. We eventually want a leading 1 in each of the first non-zero spots, but that's the last thing to worry about. We could multiply row 2 by negative 1. We could divide row 3 by a 3. Oh, excuse me, that would be multiplying row 3 by 1/3. But again, we're all friends here. We'll just say it either way. Those would help reduce some of these numbers, but again, we can save that kind of detail for the end. My main interest right now is, having done that 0 and that 0, let's put this 0 in place. Now notice that we don't want to involve row 1 anymore, because if I start taking multiples of row 1 and using that to help replace the other 2 rows, I'm going to ruin these 2 zeros that I just put in place. So to introduce a 0 where this -6 currently sits, I only want to use row 2 and row 3 together so that these 2 zeros don't interfere with one another. So let's see. What if we took -6 times row 2 plus row 3? And that will go where row 3 currently sits. There's a good bit of rewriting in this. And now I'll leave room for our brand new shining row 3. So -6 row 2 plus row 3. In the first entry, -6 of those plus that, well, that's still 0. That's good. -6 of those, so +6 altogether, plus -6. -6 of those, so -12, plus 16, is 4. And then -6 of those, which is still 0, plus that. There we go. And again, checking against the gold standard. So far, so good. Now we've introduced all the zeros where we would like them, and now we can go back and worry about making those leading non-zero entries a 1 in every row. And that's pretty simple. How about negative row 2 in place of row 2? Technically, that's a linear combination of row 2. And how about 1/4 of row 3 going in for row 3 itself? That is a linear combination of row 3. It's not much of one, but it is. If you want to know what linear combination means, go look it up. So there I've taken row 2 and just multiplied down the line by -1. And now I'm going to go down row 3 and I'm going to multiply by 1/4 in every spot, and oh, we just made a fraction. But at least we saved it to the end, and there's nothing you can do about that. It is what it is. This is now in row echelon form.